Good morning. We are today moving on into chapter 42. Chapter 42 is going to be our second chapter on physics of the nucleus. So this chapter is going to focus, last chapter we looked at properties of the nucleus, radius, talked about wave functions for the protons and neutrons a bit. Now what we're going to do is look at some of the applications in nuclear physics, looking at different types of nuclear reactions, fission and fusion reactions as sources of energy, and then also radiation effects on materials. So let's get started. Chapter 42, our second chapter on nuclear physics. So now what we're doing is we're going to start this chapter out looking at what we're going to call nuclear reactions. Now, all the stuff we've been looking at, all the reactions, the radioactivity reactions, those are radioactive decays. Now we're thinking of how we could actually set off some kind of a reaction rather than just waiting for something that's radioactive to decay. So here's our first example. It says what we're going to do is we're going to take a helium-4 nucleus and run it into a nitrogen-14 nucleus, and it says this is one of the possible outcomes. So, in a chemical reaction, you've got these different nuclei, I guess, and they're exchanging electrons back and forth and forming different chemical bonds. But in chemical reactions, you never actually change the configuration of the nuclei. In nuclear reactions, you do. So what's happening here is, look, we're ending up with fundamentally different nuclei. Protons and neutrons now are being exchanged in and out of the nucleus to give us completely different elements. So these reactions tend to be much higher energy, kind of what we saw in the last chapter. And let's take a look at this reaction in some detail. The first thing, though, I guess before we do that is let's just count protons and neutrons. So in most of the reactions that we look at, what's going to happen is the number of protons and neutrons are going to be conserved. We've seen examples in beta decay in using the weak force where numbers of protons and neutrons weren't conserved. They were being turned into each other. But in many of these reactions we look at, the number of protons and neutrons are individually conserved. So what we've got here is a pair of 2 protons and 2 neutrons combining with this nitrogen, which is 7 neutrons and 7 protons. When they collide together, we've got a combination of 9 protons and 9 neutrons available. How are they going to separate? And what this is saying is they run together, and just one of those protons separates off. So I started with 9 protons and 9 neutrons in this configuration. One of the protons leaves, and what's left is the remaining 8 protons and 9 neutrons. So again, you can kind of count protons and neutrons in some of these reactions. Now, let's diagram this out just a bit differently. How would we actually build an apparatus to set off this kind of reaction? And it's very likely that we could get a beam of helium nuclei. So it could be alpha particles. It could be that we're taking something radioactive and using that as a source of helium nuclei to set off these reactions with the nitrogen. So in these reactions, when we see helium-4, that often is just saying it's an alpha particle, and it's got 2 positive charges on it. The hydrogen that we see in these reactions often is just a proton. So again, the electrons are going to be mostly spectators in these reactions. Now just a note here, the slides that we have here are emphasizing this approach, thinking of this in terms of neutral atoms. And the text actually prefers writing in things like alpha and proton. Now, the approach in calculating energy for these, we want to put everything back as neutral atoms. Putting everything back as neutral atoms is going to make sure that we get the electron counting correct. So let's calculate a Q value for this. So for this reaction, we can start with all the materials that are going into the reaction, take a look at their masses, and then we can take a look at the masses of the nuclei that are coming out of the reaction. And so I've got to go to Appendix F or go online somewhere and look up the mass for each one of these isotopes. And so I looked them all up. There are the masses of the helium-4, the nitrogen-14, the oxygen-17, and the proton, or the hydrogen-1. And that is hydrogen-1. It's not a proton mass. That includes the electrons again, so all the electron balancing is correct. Everything here is a neutral species, so we're charge balanced. When I calculate the Q value for that, what I run into is I actually get a negative value. So what it's saying is the stuff that we're producing has more mass than what we started off with. And you're thinking, wait a minute, that's not how it worked back in the previous chapter. When things underwent radioactive decay, the mass always went down. But in this case, the mass goes up. Now, how is that possible? And so what's going to happen here is, in order for this reaction to occur, it can't be that the helium-4 and the nitrogen-14 are not moving very fast. We actually have to put a lot of kinetic energy into the reaction. So in these reactions, in this reaction in particular, we're going to have to put kinetic energy in. Some of that kinetic energy will be converted into mass. So we can set up a diagram. Let's see, the Q value here, there it is in atomic mass units. I'm using my 931.5 MeV and converting that into MeV. So it's saying that since there's a minus sign there, energy is not being released, I'm going to have to put that much energy in to the reaction. So here's the reaction profile. The way we're going to represent that is this level is representing the combined mass of the nitrogen-14 and the helium-4, and this level is representing the combined mass of the oxygen-17 and the hydrogen-1, and that's at a higher mass, and so we're going to have to put energy in. Now that represents the Q value for this reaction. So Q is negative in this case, and that means that this side is going to be higher. Now there's a second thing we got to think about. So the first item was the Q value, and we've identified that, yeah, we're going to have to put kinetic energy in for sure, because we've got to get more mass, and that kinetic energy will get converted. But there's a second issue in these nuclear reactions we have to think about, and that is the activation energy, or the potential energy barrier. There's an electromagnetic potential energy associated with bringing two positive nuclei close to each other. So here's one nucleus, let's say that's the nitrogen-14, and here comes this other helium-4 nucleus. As it gets closer and closer, as it makes its way through all the surrounding electrons, it begins to feel the full effect of those 7 protons. So the helium's coming in with 2 protons, the nitrogen's got 7 protons, and they're going to repel each other. So I can't send this in at constant speed. You know, if I send this in at some speed, it's going to slow down and get pushed away. I'm going to have to send it in at a high enough speed to overcome that potential energy barrier. Now the idea, kind of the assumption we work from, is that I need to give it enough kinetic energy that it can just barely reach the other nucleus. So it's slowing down, getting repelled, but it's close enough that the strong force can cause the reaction to take place. So we use this idea of just touching. The 2 nuclei just touch. This is our diagram that we use. Let's say this is the helium, this is the nitrogen, and each of them have an effective radius based on how strong forces work, based on how spread out their wave functions are. If I take a combined distance, center to center, between the 2 nuclei, I'm going to call that R. That's going to be the combination of the individual radiuses, and I can use that R to plug into my potential energy formula. So that's a formula we're picking up from Physics 4B. K here is the electromagnetic force constant, and the Q1 and the Q2 in this case are going to be the two nuclei, 2 point charges basically. And those are going to have charges of 2 times E and 7 times E, where E is the fundamental charge. So this is the atomic number for the helium, the atomic number for the nitrogen. So that takes care of calculating the Q's up on top. Now the R's down below, we said that we want to get a center-to-center distance. That's what the potential energy formula looks like from Physics 4b, looking at potential energies with electric forces. So what we're going to do is go back and use that radius formula that we learned in the last chapter. So in the last chapter we talked about, kind of the spread of the nucleus can be represented by 1.20 femtometers. That is our reference radius. And maybe go back and, if you don't remember, go back and take a look at some of those notes from the previous lecture. I'm going to put in 4 and 14. So what we put into that is the nucleon number. We put in the number of nucleons because we said the size of the nucleus is going to depend on how many nucleons we have. And then we take that to the 1/3 power. So we're saying that the helium-4 has probably an effective radius of 1.90 femtometers, and the nitrogen-14 has an effective radius of 2.89, and we add those together and get 4.80, and the reason that doesn't look like it adds up is because I left those numbers in my calculator. So these had more digits. Anyway, so it worked out to be 4.80 femtometers from center to center. So I need to get the two nuclei close enough to each other that center to center there's a separation of 4.80 femtometers. So let's calculate how much potential energy that might be. The potential energy then is, here's that factor of 2 and 7 from the number of protons in each of the two nuclei. That's going to leave us with a factor of Ke squared, where again, K is the electromagnetic force constant. Let me reference you guys back to chapter 21, 8.99, 10 to the 9th, newtons times meters squared over coulomb squared. This is a shortcut. I think we used this in the last chapter. K times E squared can be combined, written as 1.44 MeV times femtometers. It's kind of like our HC equals 1240 shortcut. So in a lot of these problems, we'll see a Ke squared, and we can take the combined Ke squared and write those in the units that are going to make the most sense for nuclear reactions. So for nuclear reactions, the units of MeV are going to make sense for energy. These are going to be very energetic reactions, and the distances involved are going to be of the order of femtometers. That's the scale at which the nuclear force will create these sorts of reactions. So I put all the numbers in, I put the R in down below, and it says that there's a potential energy barrier of 4.20 MeV. So we put that into the reaction profile and said, look, in order to get these two close enough that they can react, I actually have to get over this even higher barrier. It's not enough just to come up with this 1.193 MeV of kinetic energy. I'm going to need, in some way, some combination of the kinetic energy of these two to be at least 4.20 MeV. That's going to be the threshold at which we can get this reaction to occur. So again, these reaction profiles are important. Practice, we're going to look at several examples. Start looking at drawing these out. So be prepared to draw reaction profiles, and the items that we want to include in that are the Q values, which are here, and the potential energy barrier, which is here. That U needs to get written in right there. So maybe put some arrows in there and draw U the symbol U to represent the 4.20 MeV. All right, questions? Let's look at another reaction. So this is, I think, this is a good example. This is a good one to pay attention to. All right, here it's talking a little bit about some of these other types of, anyway, it gives us another reaction. That's pretty much all they're saying in here. So here's another reaction. Now this time, we're starting off with a neutron, and we have this oxygen-16 nucleus. So that's the most common isotope of oxygen, is oxygen-16. So we're going to start off with this bundle of protons and neutrons. So an oxygen nucleus, oxygen-16 nucleus, 8 protons, 8 neutrons, all overlapping each other in their wave functions in the nucleus. And then one more neutron comes in, and that makes it oxygen-17. But then one of the neutrons and one of the protons separate as a bundle. They come off as hydrogen-2. So yeah, the proton and the neutron count work. And that was actually, if you go back and look, part of the question, the first part of the question said, what would be the nucleus that would be generated in this reaction? It turns out it's nitrogen-15. Now, we're going to do the same thing we did last reaction. Let's look at the Q values here. So the Q value for this is going to be taking the mass of the nitrogen plus the mass of the oxygen, combining those together, and then subtracting off the mass of the nitrogen-15 and the hydrogen-2. Now when I did that, checked and put these masses in, I found a pretty big mass difference. And it turns out that the mass of the products, once again, are higher. In fact, this time much higher. So in fact, double check my numbers. I checked this several times. I think this is right, but this is a large amount of difference. So in this problem, we've got to create something with a lot more mass. We're going to need 9.90 MeV of kinetic energy in order to have this reaction take place. Okay, that's a really lot of kinetic energy for one of these reactions. Now, so here's our profile, and it's saying I'm starting off with a neutron and oxygen-16, and oxygen-16 is really stable. So oxygen-16 has a relatively low mass for 16 nucleons. Nitrogen-15, not quite as stable, and deuterium, it turns out, isn't very stable at all. So not a lot of binding energy there, and I think that's why the Q numbers here are so large. The deuterium doesn't represent a lot of binding energy. So that's quite a difference, 9.90 MeV. Now the second step that we've got here would say, okay, what kind of an activation energy might we have? Remember, on that last example, it wasn't enough to be able to just get enough energy to create those products. We actually had to get over this potential energy barrier. Well, this time, there's no potential energy barrier. And that's because we started off with a neutron. So, you know, any kind of a nucleus that runs into another nucleus, they're both going to be positively charged. But if we run a reaction entirely with neutrons, neutrons can find their way in, no problem. So the neutrons, there's no repulsion, and the neutrons can just set off these reactions very easily. A neutron can find its way in and react with a nucleus without any of the potential energy barrier from the electric force. So that was easy enough. U is equal to 0, that's a non-issue here. And that leaves us with the combined kinetic energy of the neutron coming in, plus possibly the kinetic energy of the oxygen. You know, we could have the oxygen sitting there at rest and the neutron come in, or we could have them both headed towards each other. But the threshold energy in this case, 9.90 MeV. So that's a lot, and it's entirely due to creating that extra mass that we have on the side of the products. All right, so what they're looking at here on this slide is they're just outlining the same stuff we've already been doing. What they're saying is that when you run these kind of transmutation reactions, so transmutation sounds pretty awesome, right? What that really says is that we're converting one element to another, and the only way you can convert one element to the other is change the number of protons inside there. Or, I guess more generally, change one isotope. We're changing isotopes around, rearranging how the neutrons and protons are packed together. And here again, it's just saying, reminding us that we're used to thinking of Q as being positive, and that the reaction is giving off energy. It's exothermic. But now we're seeing examples where Q is negative. And when Q is negative in a problem, it just means that the reaction is going to require an energy input to create something with more mass to it. All right, here's another reaction, another nuclear reaction. It looks like, once again, what we're doing is we're setting this off using a neutron. The target, the nucleus in this case, is boron 10, and it says that this reaction is going to proceed and, well, let's see what happens here. With the boron 10, I got 5 protons, 5 neutrons, all bundled together, overlapped with their wave functions. Another neutron comes in, joins the whole group, and then they separate out. 2 protons and 2 neutrons come out as one bundle, and then the remaining 3 protons and 4 neutrons are the separate bundle. And we call those lithium and helium. So, now they've given us some numbers here. It's kind of like they've given us almost too much information in the problem. So, there is one of these numbers. Let's see, they gave us a couple of the masses. This number right here. So they said that the outgoing helium is observed to have a speed of 9 times 10 to the 6 meters per second, and that the neutron coming in is essentially at rest. So they say that the neutron coming in does not come in with a significant amount of kinetic energy. Let's see how this plays out with our calculations here. So here's another nuclear reaction. And we've just drawn the same nuclear reaction that they gave us. We've looked up the 4 items, not in the periodic table. We've looked these up in an isotope table, Appendix F, or going online. And those are all out to 6 significant figures. And we're paying attention as we go along to see if any crazy numbers pop up, if we've made an error. Here's how we calculate Q's, taking the mass of what we start with, the mass of what we're left with. This time the Q's coming out positive, 0.002997 atomic mass units. We convert that into an equivalent amount of energy. And it says, hey, this time we do release energy. So there's kinetic energy from this. And the kinetic energy combined, we've got 2 products coming out. And the combination of their 2 kinetic energies are going to be 2.79 MeV. That's the Q. That's the available energy that's being released. Now, so for this process then, we can draw one of these energy profiles. So our energy profile this time says, hey, this time it's the neutron and the boron 10 that have more mass, and the lithium 7 and the helium 4 that have less mass. So this is a step down in terms of mass, and that says energy will be released. What about our electric potential energy barrier? What textbooks refer to as Coulomb barrier. So the barrier created in this case is none, and again that's because we have a neutron coming in. So these neutrons can come in without any kind of a potential energy barrier. No electric force or electric potential energy, no electric repulsion taking place. So we're done. We don't have an activation energy. This thing can just drop off. Once the neutron comes in, it can set off the reaction. That's going to be easy enough. And then we're going to release a bunch of energy. So no kinetic energy needed up front. the neutron can come in at really low speeds. It will be what's referred to as a slow neutron, if you look at that previous slide. Now what we can do, this opens up a possibility of, hey, we could go back and use some of those formulas that we had developed back in special relativity, saying that if I start with an object with mass m naught, and it divides into two pieces, mass m1 and m2, I can figure out how the kinetic energy divides up between the two products. So what we could do is, so we could assign some numbers here. The starting mass is going to be the combined mass of the neutron plus the mass of the boron. So I've got the neutron and the boron mass combined as 11.021603. I can treat it as if it's one combined object once the neutron comes in and sticks. The mass of the products, I'm going to say object 1 or particle 1 is the lithium, particle 2 is the helium, and these are the masses of those. And if you remember back, I guess it was just last chapter, we went in and we solved the kinetic energies back when we were looking at alpha decay. So those are the kinetic energy formulas that we derived last chapter, and we can plug into those. We've got the Q value already, we've got all the masses, so we just follow the prescription that we've set up here, take those masses, plug into this formula. The Q contains the MeV units, and the mass units of atomic mass units, they're all going to cancel out. So what we find is that, let's see, our prediction, well, what we found in our formulas, it's always the lighter object that gets more of the kinetic energy. So in this case, we're guessing that the helium-4 is going to end up with a larger portion of the kinetic energy compared with the lithium-7. And so we plug all the numbers in, and sure enough, it says that about 36% of the energy is going to the lithium, and 64% is going with the helium. So taking that 2.79 and dividing it out, turns out that's how the kinetic energy divides up. So 1.01 MeV goes with the lithium, 1.78 MeV goes with the helium. Now, what we can also do is, since we now know the kinetic energies for the lithium and the helium, we can do a velocity calculation. You know, one of the things I always miss in these chapters is there's all this energy, kinetic energy stuff, and sometimes you just want to know how fast these particles are going. And so what we can do is this. I'm going to go back to classical physics formulas for kinetic energy. In the last chapter, we did a couple of these examples, and we used relativity all the way through. But what we found was, typically, even though these are very energetic reactions, and the pieces coming out are going at really high speeds, they're still not really so close to the speed of light. And we can get away with using classical formulas. In fact, in some ways, the classical formulas allow us to, using an approximate formula, allows us to get a better measurement of the velocity, because some of the relativity formulas run into numerical issues with trying to keep too many significant figures. Anyway, so here's our alternate formula for not using relativity, but we're going to go back and use classical formulas. K is equal to 1/2 mv squared. That's the formula everybody remembers from physics 4a. I'm going to flip that around and solve for v. The speed of an object 2 times its kinetic energy over mass square root. And then I'm going to put some factors of c in and say the velocity is equal to c times 2k over mc squared square root. Now you might look at those factors of c and go, well, isn't that relativity? And you go, no. It actually is a classical formula written in a manner to enable us to put the numbers in easily and get the results. So rather than trying to get masses in kilograms and whatever, what we can do is this. We've got the kinetic energies. Those are already in MeV. And the way we can get the masses is we can take these atomic mass units for these, we can take these atomic mass units, multiply them by 931.5. So to get the mass numbers down here, again, what I want to do is take this number, multiply it by 931.5. That's going to tell me the mass equivalent, and that's what goes into the calculation. Same thing with the helium, 4.0026 whatever. Multiply that by 931.5. Put that number into the denominator. Don't forget the square root sign. And what I ended up with, check my numbers, was C times 0.0176. So yeah, it's about 1.76% the speed of light. And that works out to be 5.27 10 to the 6 meters per second. So this is fine. You can look at that and go, wow, that's like 1,000,000 meters a second, like 5 million meters a second. That's really fast. And again, you can look over here with the factor of C attached and go, oh, what is it relative to the speed of light? Well, it's 1.76%. Now that was the lithium. For the helium, we do the same calculation and find out the helium's going even faster at about 3% of the speed of light, or about 9 million meters per second. So kinetic energies, velocities, this is another good example to take a look at and make sure you're understanding how these work. One more reaction we've got here. So they're giving us another example. They're saying here's a proton coming in, and here is carbon-13, and here is nitrogen-13, and there's a neutron that comes out. And they're saying, will this reaction happen if the protons come in with 2 MeV? So they're asking a question, is 2 MeV going to be enough kinetic energy to have this reaction happen? So there's two things we got to look at. We've been seeing this in the other examples, so we're experts at this now. Here's the reaction they've given us. I'm going to rewrite that proton as a hydrogen 1. And again, what we're doing is we're balancing electrons. When I look up these masses, what these masses are assuming is that all of their electrons are in place. So the way I can make sure that the electron count is correct is to think of all of the reactants and the products as being neutral atoms. Okay, now in reality it's just the nuclei that are reacting. But again, to get the masses correct, I want to write everything down as a neutral atom. Alright, so let's do a Q on this. This is the mass of the hydrogen plus the mass of the carbon, subtracting off the mass of the nitrogen and the mass of the neutron. We got a minus sign. So the minus sign is telling us, and this is minus 3.00 MeV, the minus sign is telling us once again we're creating something with more mass. That additional mass is the equivalent of 3 MeV of energy. So here is the starting materials, and here are the products coming out, and we got to get up by 3 MeV. 2 MeV is not going to be enough. So 2 MeV is not going to get this done. It's not going to work. So we're going to have to go up to at least 3 MeV. Now there's a second question that we have to ask, and the second question is, well, sure, I got to come up with 3 MeV to create that extra mass, but is there a potential energy barrier that I also have to get past? How high would a potential energy barrier be between a hydrogen nucleus and a carbon-13 nucleus? So let's do that. Here's our formula, K Q1 Q2 over R. And I'm going to do this little shortcut. We've done this in a previous example. What I'm going to do is write this. Here's my Ke squared. Here are my 2 atomic numbers. So what we found was the charge on each of the nucleus can be written as the atomic number times the fundamental charge. And so I'm going to get a factor of Z1 and a factor of Z2. Those are written right here, 1 and 6. 1 for the hydrogen, 6 for the carbon. And then the Ke squared shortcut is 1.44 MeV femtometers. And then for the combined distance, yeah, I got the picture here. So here are the two nuclei. I'm going to get a center-to-center distance measurement, and that's going to be adding the two radiuses together. And the individual radiuses are going to be given by R0 a to the third, R0 a to the third. Ooh, that should have an A1 in it. That should have an A2 in it. Write those in. And so I put those up here to combine them. So I'm putting all the numbers in, but R0 is the 1.20 femtometers. The total number of nucleons for the hydrogen coming in is just 1, but for the carbon-13 it's 13. Now, I don't know why this says 1 over 13. It should be 1/3. There we go. Okay, 1/3. And what I'm finding is that there's a potential energy barrier of 2.15 MeV. Well, that becomes kind of a non-issue because we have a mass barrier of 3.00 MeV. So, electric force barrier, 2.15 MeV, mass barrier, 3 MeV. So our reaction profile looks like this. By the time I've gotten up to enough kinetic energy to generate the additional mass, I've already taken care of the electric barrier. So that becomes a non-issue for us. So, final answer here, proton coming in at 2 MeV, not going to get things done. We're going to need 3 MeV if we're going to be able to set off this reaction. Again, I don't know where that came in. Like, I know what it looks like. It looks like it came in from the 13. All right, make that adjustment, cross that out. So here's an interesting example of transmutation of elements. If we take uranium-238 and we add a neutron to it, so these were reactions that were done back in the 1930s or something, and these were actually done here at UC Berkeley at the Lawrence Berkeley National Lab and on the UC Berkeley campus. So there were accelerators that were being built. At first the accelerators were pretty small, and then they got bigger and bigger. What we could do is we could take neutrons, combine those with uranium-238, and that would create uranium-239. Now, the neutron captured by the uranium-238 creates the uranium-239. The uranium-239 is not stable, so it undergoes radioactive decay. It turns out that uranium-239 actually undergoes beta decay, beta minus decay. And that means that it goes from element 92 to element 93. So those early experiments in taking neutrons and running them into things and then looking to see what you may have generated led to the creation of a new element that basically doesn't exist on Earth. And the reason why is neptunium, the isotopes of neptunium have short half-lives. It's probably there was never very much in the solar system, and that the neptunium had a short enough half-life that it's basically all gone. So researchers at UC Berkeley identified these new elements, neptunium. Now what the neptunium would also do is the neptunium also beta decays, and it creates plutonium-239. Now these are beta decays, they're giving off electrons and antineutrinos, and that's how researchers first generated the first trans-uranium elements by looking at neutrons to set off these sorts of reactions. Now when we get into nuclear fission, which we're going to do in just a bit here, we're going to find out that this becomes an important reaction for the possibility of using nuclear fission power plants, for example. It turns out that uranium-238 does not undergo nuclear fission. Its isotope uranium-235 does. But uranium-238 can easily be converted by these reactions, can be converted into plutonium-239, and plutonium-239 also is a possible fuel for a nuclear fission. So the idea would be then to take existing uranium-238, convert it into plutonium-239, and you're generating a lot of additional nuclear fuel for a fission power plant. And let's take a look at nuclear fission. So now we're at the point where here is kind of a diagram of what happens in nuclear fission. Turns out that uranium-235, that particular isotope of uranium, when it absorbs a neutron, it ends up destabilizing the nucleus. So you get this excited version of uranium-236. Now, instead of just giving off a little piece of something to settle back down, the excited uranium-236 splits into two pretty good-sized pieces. So this is quite different from the radioactive decay reactions that we looked at in the previous chapter. So in nuclear fission, we get two really large-sized nuclei coming out, and then we also get neutrons coming out. Once you get far into the periodic table, we've looked at this before, where as you get farther and farther into the periodic table, you need more and more neutrons to stabilize the nucleus. And so these fission reactions release additional neutrons, which can react with other nearby uranium-235s. So in some sense, it's kind of a self-sustaining reaction. If you have a collection of uranium-235 nuclei, and you set one of those off, the reaction can take it from there. So the reaction generates its own additional neutrons, which can set off the reaction. So here's an example of a nuclear fission reaction. In the reaction that we have right here, what we're doing is we're starting with uranium-235. We're bringing a neutron in. Again, the neutron's not going to experience any electric repulsion, and so a neutron can easily find its way to the nucleus. And when it does, it breaks into two kind of large pieces. Now here they've actually turned this into a problem. They're saying in this particular fission reaction, where the nucleus splits into pieces, it releases two neutrons, and then it releases two different nuclei. One of those is strontium-93. They want you to figure out what the other one is, so let's go ahead and look at that. So here's the reaction that they've given us. Now for nuclear fission, all that's happening are the protons and neutrons are being rearranged. So if I count numbers of protons and count numbers of neutrons and make them match before and after the reaction, that'll solve the problem. So it turns out that I started with 92 protons. The strontium accounted for 38 of those protons. So there were 50, I hope that's right, 54 missing. So the element we're looking at is xenon. So it's split into two pieces. One of those had 38 protons in the bundle, and the other bundle had 54 protons. This one's going to be an isotope of strontium. This one's going to be an isotope of xenon. And then if we count the total number of nucleons, there was 1 plus 235, that's 236 nucleons that went into the reaction. Well, there's 2 of those are here, 93 of those are here. The remaining bundle is going to be 141. So there's an example of a fission reaction. Now, with fission, there are like hundreds of different possible outcomes. Even though we start each time with kind of the same reaction, we send a neutron in and it reacts with the uranium-235. The uranium-235, with the neutron added, it can split into many different possible ways. But characteristically, what we end up with are two, pretty good-sized nuclei. And we typically end up with more than two. This is a low number of neutrons coming out. I think on average it's like 3 or 4 neutrons that come out of each reaction. And so some number of neutrons will also come out of the reaction. So that's what the nuclear fission looks like as an example. So let's run through a few of the numbers here. So if we were to look for an energy number, how much energy is being released in this reaction, then what we would want to do is start off with the mass of everything going in. So we want to include the mass of the neutron, mass of the uranium. Now I've written down the masses of the uranium, xenon, and strontium, and we had the mass of the neutron on some previous examples that we looked at. So I'm adding those two masses together, subtracting off the masses of the xenon, the strontium, and the additional neutrons that were produced. And what I found was I ended up with 0.194588 atomic mass units, multiplied that by our 931.5 energy converter. The Q on this is 181.3 MeV. That's a lot. If you think back to the radioactive decay processes, the radioactive decay processes we looked at, an energetic alpha decay might release 4 or 5 MeV. This is 181, so I had to write down wow with an exclamation point. So how much, what fraction of the mass has been converted into energy during a reaction like this? Because what we're seeing, and this is like, 40 or 50 times as much energy as any other reaction that we've looked at so far. So this really is going to release a lot of energy. So I did this calculation. What I did was, what fraction of mass is being converted to energy? So I took the Q coming out, how much energy is there, or I could have used its mass equivalent. And then for the uranium, I took the 235 atomic mass units and used my 931.5 multiplier to determine how much energy is that equivalent to. And then the MEVs cancel out. So again, what I'm thinking of the investment we made was really just the uranium-235, and that's because once the reaction gets going, the neutrons are for free. I don't have to keep generating additional neutrons. So here is the energy equivalent of the mass 235 to start with. Here is how much kinetic energy we get in the reaction. 0.000827, or about 1 part in 1200. So what I'm getting to here is we're starting to get, now 1 out of 1200 might not seem like much, but that's a pretty measurable, significant amount of the mass that disappears in this reaction. If we had, for example, if we had a kilogram of uranium-235 that we started with, that would create, if I ran this reaction using a full kilogram, almost a gram of mass would go missing. That's something we could measure, right? If we start with 1,000 grams of uranium, and the products are only 999 grams. There's literally a gram missing from that. So if I take that fraction, the 0.827, it makes this prediction. It says that for a kilogram of uranium, let's say we build a power plant, we use that reaction in our fission power plant, the uranium fission reaction. If I take that 0.827 grams and just use a formula E equals mc squared, and plug it in, it works out to be 7.44 10 to the 13th joules, 74 trillion joules of energy. Hard to judge what that is, but it turns out that's a lot of energy. In fact, that much energy, if we charge 20 cents per kilowatt hour, and you guys can go in and do the conversions on this if you want and check. My calculation came up as it's $5 million worth of electricity from just 1 kilogram of uranium-235, and uranium's pretty dense. A kilogram of uranium-235 could be a pretty small piece. So there is a lot of energy available through nuclear fission. So that's probably a good time to stop. I think we're coming up on a good time to take a break here. So let's take a break and then we'll come back, pick up maybe from this example, and then move on and say a few more things about our nuclear fission reaction.